Hi, my curious friends. Welcome to my channel. Have you ever had one of those afternoons that just drags, where you're watching the clock, waiting for the day to end, and each tick of the second hand feels like a tiny, sluggish eternity? Or, on the flip side, have you ever been so completely lost in a conversation, or a book, or a moment of pure joy, that hours seem to collapse into what feels like minutes? You look up, startled, and the sun has set without you even noticing. We've all felt that. This strange, elastic quality of time in our minds. It speeds up, it slows down, it warps and bends based on what we're doing, how we're feeling. It's a trick of perception, of course, a quirk of the human brain. The clock on the wall, we assume, keeps ticking away with its perfect mechanical regularity. 1 second per second. Always. But what if I told you that the clock itself is in on the trick? What if the very flow of time, the river of seconds and minutes that we all float down from birth to whatever comes next, isn't a constant, steady current at all? What if it's more like a chaotic, churning stretch of white water where the flow speeds up and slows down depending on where you are and what you're doing? This isn't a philosophical idea. It's not science fiction. It is cold, hard, experimentally verified scientific fact. It's a phenomenon so strange, so counter to everything our daily lives teach us, that it feels like it must be magic. But it's not magic. It's physics. It's called time dilation. And for the next little while, I invite you to forget everything you think you know about time. Let's set aside our calendars and our wristwatches, and let's dive headfirst into the true, weird, and breathtakingly beautiful nature of reality. We're going to pull back the curtain. We're going to follow the threads of this mystery, from a brilliant patent clerk with wild hair to the most accurate clocks ever built, to the very edge of our understanding of the cosmos. We are going to chase this idea until there is not a single stone left unturned. So, get comfortable, take a deep breath, and let's begin our journey into the stretched and squashed fabric of time itself. Our story really starts not with complex mathematics, but with a very simple, very fundamental question. What is light? For centuries, this was one of the great puzzles of science. Isaac Newton, the colossal figure of physics, thought light was made of tiny, tiny particles. Corpuscles, he called them. He imagined them streaming from the sun, bouncing off objects, and flying into our eyes. Others, like the Dutch scientist Christian Huygens, argued that light was a wave, like a wave on the surface of a pond. It rippled through an invisible, mysterious substance that filled all of space, which they called the luminiferous ether. Think of it as an invisible cosmic jelly that vibrates, carrying light from the stars to us. For a long time, the wave theory seemed to have more evidence. Light exhibited interference and diffraction, classic hallmarks of wave behavior. If you throw 2 stones into a pond, the ripples from each stone will spread out and eventually meet. Where a peak from one wave meets a peak from another, they combine to make a bigger peak. Where a peak meets a trough, they cancel each other out. Light does the same thing. Shine it through 2 narrow, closely spaced slits, and you don't get 2 simple bars of light on a screen behind them. You get a beautiful, shimmering pattern of bright and dark bands, an interference pattern that can only be explained if light is a wave. So by the late 1800s, the scientific community was largely convinced light was a wave, and waves need a medium to travel through. Sound needs air, water waves need water. So light, it was reasoned, must need the ether, This ether had to be everywhere, permeating the vacuum of space, flowing through the air, passing through our very bodies. It had to be utterly frictionless, completely undetectable by any ordinary means, yet stiff enough to allow light to travel at its immense speed of about 186,000 miles per second. It was a strange concept, but it was the best one they had. This is where our story gets interesting. Two American scientists, Albert Michelson and Edward Morley, decided to try and prove the existence of this ether once and for all. Their reasoning was brilliant. Imagine you're on a boat on a river. The river current is the ether wind flowing through space. If you swim directly downstream, your speed relative to the riverbank is your swimming speed plus the current's speed. If you swim upstream, it's your speed minus the current. But if you swim directly across the river, the current tries to push you sideways. To get straight across, you have to angle yourself slightly upstream. This means it takes you longer to swim across the river and back than it does to swim the same distance downstream and back upstream. Michelson and Morley built an incredibly sensitive instrument, an interferometer, to do this with light. They reasoned that as the Earth orbits the Sun at a dizzying 67,000 miles per hour, it must be moving through the stationary ether. So, there should be an ether wind blowing past us. They would split a beam of light, send one part in the direction of the Earth's motion, and the other part perpendicular to it. Just like the swimmer in the river, the two beams, when reunited, should have taken slightly different times to travel their paths due to the ether wind. This would show up as a shift in their interference pattern. They performed the experiment. They checked and rechecked. They rotated their apparatus. They tried it at different times of the year. The result was nothing. No shift. No ether wind. It was as if the swimmer, in our analogy, took exactly the same time to swim across the river and back as he did to swim upstream and downstream. The experiment was a stunning failure. It was, in the words of one physicist, the most famous failed experiment in history. This was a crisis. The foundation of classical physics had been shaken. How could light be a wave if there was no medium for it to wave in? The ether, this invisible cosmic jelly, seemed to not exist. The scientific world was baffled. The stage was set for a revolution, and the revolution came from a most unlikely source. A young man working in the Swiss patent office in Bern. His name was Albert Einstein. In 1905, his so-called miracle year, Einstein published a series of papers that would change the world forever. One of them was on a theory he called the special theory of relativity. It started with two deceptively simple postulates, two assumptions that he asked us to take as true, and then to follow their logic wherever it led, no matter how strange the destination. The first postulate was the principle of relativity. This wasn't entirely new. Galileo and Newton had talked about it. It simply says that the laws of physics are the same for everyone, no matter what their state of uniform motion is. If you're in a spaceship moving at a constant speed in a straight line, with no windows, there is no experiment you can do inside that spaceship to tell if you're moving or standing still. You can drop a ball, it falls straight down. You can play pool, the balls bounce as expected. It feels exactly the same as if you were parked in a hangar. Only when you accelerate, when you speed up, slow down, or turn, can you feel the motion. This is why you're pressed back into your seat when a car accelerates, or flung to the side when it takes a sharp corner. But constant, steady motion is undetectable. It's all relative. The second postulate was the bombshell. Einstein stated that the speed of light in a vacuum is constant. It is always the same for all observers, regardless of their own state of motion. Let that sink in for a moment. Imagine you're standing still, and I flash a light. You measure its speed. It's 186,000 miles per second. Now, imagine your friend is in a super-fast rocket ship, flying at 100,000 miles per second towards the source of that light. What would you, with your classical intuition, expect your friend to measure? You'd think he'd measure the speed of the light beam as his own speed, plus the speed of light, right? 100,000 plus 286,000 miles per second. But Einstein says no. His second postulate says your friend, with his super-accurate instruments, will measure the speed of that very same light beam as exactly 186,000 miles per second, not a fraction more. Now imagine another friend in a rocket ship flying away from the light source at 100,000 miles per second. Classical intuition says she should measure the light speed as 186,000 minus 100,000, which is 86,000 miles per second. But again, Einstein says no. She will also measure it at exactly 186,000 miles per second. This is utterly bizarre. It defies all common sense. How can everyone measure the same speed for light, no matter how they are moving? It's like if you're driving a car at 60 miles per hour and another car passes you, also going 60. Relative to you, it seems to be crawling past. But if that car were a beam of light, it would still streak past you at 186,000 miles per second, even if you yourself were going 185,999 miles per second. It makes no sense from our everyday perspective. But Einstein accepted this as a fact, based on the Michelson-Morley experiment and other work. The speed of light is the universe's ultimate speed limit. And it's the same for everyone. It's a cosmic constant. And from this one, simple, strange fact, everything else follows. It's like a single loose thread on a sweater. When you pull it, the entire garment begins to unravel and reshape itself. In this case, the garment is our understanding of space and time. So, let's pull that thread. Let's see what happens when we insist that the speed of light is constant for all observers. Imagine a simple clock. Not a digital clock or a mechanical clock with gears, but a light clock. This is a theoretical device that measures time using light itself. It consists of two perfect mirrors, facing each other, separated by a precise distance. Let's say the distance is exactly 1 foot. A single photon of light is bouncing up and down between them. Tick, it hits the bottom mirror. Tock, it hits the top mirror. Each round trip, from bottom to top and back to bottom, takes a specific, incredibly short amount of time. Let's call that one tick of our light clock. It's a perfect, fundamental timekeeper. Now, let's put this light clock on a spaceship. And let's say you are on this spaceship with the clock. The clock is standing upright, and you're just floating next to it, watching the photon go up, down, tick, tock, tick, tock. It's regular. It's reliable. This is your experience of time. Let's call the time between ticks, from your perspective, dt. We'll use the prime symbol to denote the time measured by someone moving with the clock. Now, here's the crucial part. I am standing on Earth, watching your spaceship zoom past me at an enormous constant speed, say 90% the speed of light. From my perspective on Earth, what does your light clock look like? As your ship flies past me, the photon in the clock is still bouncing. But it's not just going up and down anymore. From my point of view, it's also moving sideways with the spaceship. So, its path isn't a straight vertical line. It's a zigzag. It goes from the bottom mirror But by the time it reaches the top mirror, the whole clock has moved sideways a considerable distance. So, the path of the photon, from my earthbound perspective, is a diagonal line. Then it heads down to the bottom mirror. But again, the clock has moved. So that's another diagonal line. Let's draw this mentally. You have the vertical path, which is the distance between the two mirrors. That's one leg of a right triangle. Then you have the horizontal distance the clock has moved during the time it took for the photon to go from bottom to top. That's the other leg. The actual path the photon took, the diagonal, is the hypotenuse of this right triangle. Now here comes the magic and the pinch of paradox. Remember Einstein's second postulate? The speed of light is constant. I, on Earth, measure the speed of that photon. You, on the spaceship, also measure the speed of that photon. We both get the same number, c, the speed of light. But look at the paths. The path I see the photon take, the diagonal, is longer than the path you see it take, the simple vertical. Distance equals speed multiplied by time. The speed is the same for both of us, but the distance is different. The only way for the math to work out, for the speed to remain constant, is for time itself to be different for us. Let's just pause and appreciate the sheer audacity of this. This isn't a mechanical effect on the clock. It's not that the clock is broken. It's that time itself is passing more slowly for the moving spaceship relative to me. Your seconds are longer than my seconds. Your heart is beating slower from my point of view. Your thoughts are forming more slowly. The very process of aging is stretched out. This is time dilation, the stretching of time due to relative motion. This is the first and most famous form of time dilation, velocity time dilation. It's a consequence of the special theory of relativity, and it has been proven, beyond a shadow of a doubt, by experiment. The most direct and beautiful proof involves subatomic particles called muons. Muons are created high in the Earth's atmosphere when cosmic rays from space smash into air molecules. These muons are unstable. They decay into other particles after a very short lifetime. In a laboratory at rest, a muon has an average lifetime of about 2.2 microseconds. That's 2.2 millionths of a second. Even if they were traveling at the speed of light in that short lifetime, they could only travel about 0.66 kilometers, or about 2,100 feet. Yet, they are created about 10 to 15 kilometers up in the atmosphere. How do so many of them manage to reach the ground and be detected? According to classical physics, they shouldn't. They should decay long before. But they don't. And the reason is time dilation. From our perspective on the ground, the muons are moving at close to the speed of light, often 99.9% of CE or more. So their clocks are running extremely slow. In that time, traveling at nearly the speed of light, it can cover almost 15 kilometers, easily enough to reach the ground. From the muon's own perspective, it's not that its lifetime is longer. In its own frame of reference, it still lives only 2.2 microseconds. But the distance it has to travel is different. From the muon's point of view, the Earth's atmosphere is rushing towards it at 99.9% of C, and because of another consequence of relativity we haven't discussed yet, length contraction, the atmosphere is massively squashed in the direction of motion. So, from the muon's perspective, the 15-kilometer journey might only be 0.66 kilometers long, a distance it can cover in its short 2.2 microsecond life. It's a perfect, self-consistent picture. Both perspectives are correct within their own frames of reference. Time dilation and length contraction are two sides of the same coin, both stemming When they compared these clocks to identical ones left on the ground, they found a tiny but measurable difference. The flying clocks, which had been moving faster relative to the Earth's center, had experienced slightly less time. They were a few hundred nanoseconds slow, exactly as predicted by special relativity. Today, the GPS system in your phone or your car must account for time dilation. The satellites are moving at high speeds relative to the Earth's surface, so their clocks run slow by about 7 microseconds per day due to special relativity. But they are also higher up in Earth's gravity well, which, as we will soon see, makes clocks run fast. The net effect is that the satellite clocks run fast by about 38 microseconds per day. If the engineers didn't deliberately build this correction into the system, the GPS would accumulate errors of several miles per day, rendering it useless. So, every time you use Google Maps, you are personally verifying Einstein's theory of relativity. Time dilation is not just an abstract idea. It's a practical reality that your phone uses to figure out where you are. Now, this is where many explanations stop. But we promise to leave no stone unturned, and we've only covered one of the two great causes of time dilation. We've talked about relative velocity. But there's another, equally profound, and in some ways even stranger, cause: gravity. This brings us to the second act of our story, the general theory of relativity. For 10 years after his 1905 paper on special relativity, Einstein was deeply troubled. His theory was brilliant, but it had a limitation. It only dealt with constant uniform motion. It couldn't handle acceleration. And most importantly, it was completely incompatible with Newton's theory of gravity. Newton saw gravity as a mysterious, instantaneous force, acting across vast distances. Einstein found this idea deeply unsatisfying. How could the sun reach out across 93 million miles of empty space and pull on the Earth? What is the mechanism? He had a thought, perhaps his most famous thought. He imagined a man in a closed box, like an elevator. Suppose this elevator is out in the depths of space, far from any planet or star. It's floating, weightless. The man inside is floating too. Now suppose a rope starts pulling the elevator upwards with a constant acceleration of 32 feet per second squared, which is 9.8 meters per second squared, the acceleration due to gravity on Earth. What would the man inside feel? He would be pressed against the floor of the elevator, just as if the elevator were sitting on the surface of the Earth. If he dropped a ball, the floor of the accelerating elevator would rush up to meet it, making it look exactly as if the ball were falling to the floor. There would be no experiment he could do inside that closed box to tell whether he was in a rocket accelerating through space or simply sitting at rest in a gravitational field on Earth. This was the seed of the equivalence principle. The effects of gravity are locally indistinguishable from the effects of acceleration. Gravity and acceleration are, in some deep way, the same thing. This simple idea has profound consequences. Imagine that accelerating elevator again. Now, imagine the man inside shoots a laser beam horizontally from one wall to the other. From his perspective inside the box, the light beam travels in a straight line. But now, consider this from the perspective of someone outside, floating in space, watching the elevator accelerate upwards. In the tiny amount of time it takes for the light to cross the elevator has moved upwards. So, the spot on the far wall where the light beam hits is slightly lower than the spot it was aimed at. From the outside observer's perspective, the path of the light beam is a curve. It bends downwards. Now, invoke the equivalence principle. If an accelerating elevator is equivalent to being in a gravitational field, then light must also bend in a gravitational field. gravity bends light. This was a stunning prediction. Newton's theory said gravity was a force that acted on objects with mass. Light has no mass, so Newtonian gravity said it should be unaffected. But Einstein said no. Gravity isn't just a force, it's a curvature. A curvature of what? Of space-time itself. This is the heart of general relativity. Einstein proposed that mass and energy tell space-time how to curve, and the curvature of space-time tells mass and energy how to move. The force of gravity is an illusion. The Earth isn't being pulled by the sun by some invisible string. Instead, the sun's immense mass creates a well in the fabric of space-time. The Earth is like a marble rolling around the rim of that well, trapped in a stable orbit. It's moving in a straight line through a curved geometry. Think of a trampoline. If you put a heavy bowling ball in the middle, it creates a deep dip in the fabric. Now roll a marble across the trampoline. It won't go in a straight line. Its path will be curved by the dip created by the bowling ball. That's gravity. The planets orbiting the sun are doing the same thing. So what does this have to do with time? Everything. If space and time are woven together into a single fabric called space-time, then you cannot curve space without also affecting time. Gravity causes time dilation. Let's go back to our accelerating elevator. But this time, let's think about time, not light. Imagine we have two identical perfect clocks. We place one clock on the floor of the elevator and one on the ceiling. Now, we make the elevator accelerate upwards. According to special relativity, velocity causes time dilation. But here's the key insight. Because the elevator is accelerating, the two clocks are moving at different speeds at any given instant. Think about it. At time t = 0, both clocks are stationary. A moment later, the floor clock has been pushed upwards a little bit, so it has a small speed. The ceiling clock, being farther from the engine, the point of the pull, has been accelerated for a fraction of a second longer, so it has a slightly higher speed than the floor clock. A moment after that, the floor clock's speed has increased, but the ceiling clock's speed is still higher. At every single moment, the clock on the ceiling is moving faster relative to an inertial, non-accelerating observer than the clock on the floor. And since relative velocity causes time dilation from the perspective of the inertial observer, the faster moving clock on the ceiling will be ticking more slowly than the slower moving clock on the floor. Now, by the equivalence principle, this must also be true in a gravitational field. If we place one clock lower in a gravitational field and one clock higher, the lower clock, which is analogous to the floor clock in the accelerating rocket, will be ticking slower than the higher clock. Gravity slows down time. The stronger the gravity, the slower time passes. This is gravitational time dilation. Let's make it concrete. Imagine two twins, not on spaceships this time, but on Earth. One lives in a penthouse at the top of a skyscraper. The other lives in a basement apartment. The twin in the penthouse is living at a slightly higher gravitational potential. The gravity is very, very slightly weaker up there than it is in the basement. Therefore, her clock runs ever so slightly faster. The effect is tiny, but it is real. Over a lifetime of, say, 80 years, the twin in the penthouse would be about a few milliseconds older than her basement-dwelling sibling. They have actually measured this. With incredibly precise atomic clocks, scientists have confirmed that a clock placed just a foot higher on a table ticks measurably faster than one on the floor. The effect gets much more dramatic near extremely massive objects. A clock on the surface of the sun would run slow compared to a clock on Earth. A clock near a neutron star or a black hole would run excruciatingly slow from our perspective. Imagine you are watching a brave astronaut falling towards a black hole. From your safe vantage point far away, you would see strange things. As the astronaut approaches the event horizon, their signals would get more and more redshifted, and their movements would appear to slow down, like a movie running in slow motion. They would appear to freeze, hovering just at the edge of the horizon, their clock completely stopped from your perspective. You would never actually see them cross the event horizon. For the astronaut, however, nothing so dramatic happens at the horizon. They would cross it and, according to general relativity, be spaghettified by the extreme tidal forces, heading towards the central singularity. Their own clock ticks normally from their perspective until the very end. But from your perspective, their time is infinitely dilated at the horizon. This is the ultimate time dilation. It's not just a slowing down, it's a full stop. So now we have the two great pillars of time dilation, velocity and gravity, and they are intertwined in complex ways. For example, the GPS satellites we mentioned earlier are affected by both. Their orbital speed of about 14,000 km/h causes their clocks to run slow by about 7 microseconds per day due to special relativity, velocity time dilation. But because they are 20,000 km above the Earth, in a weaker gravitational field, their clocks run fast by about 45 microseconds per day due to general relativity, gravitational time dilation. The net effect is that they run fast by 38 microseconds per day. This is a constant, predictable drift that is engineered into the system from the start. Now let's address some of the common questions and paradoxes that arise from this. The most famous is the twin paradox. We touched on it earlier. One twin stays on Earth. The other twin gets in a spaceship and travels to a distant star at close to the speed of light, then turns around and comes back. Due to time dilation, the traveling twin should be younger than the stay-at-home twin when they reunite. But wait, you might say, isn't all motion relative? From the traveling twin's perspective, isn't it the Earth that is moving away at high speed and then coming back? So, shouldn't the Earth twin be the younger one? This is the paradox. The resolution lies in the fact that the situations are not symmetrical. The stay-at-home twin is in a single inertial frame of reference. We're ignoring the Earth's rotation and orbit for simplicity. They are not accelerating. The traveling twin, however, must accelerate to leave Earth, decelerate, and then accelerate again to turn around at the distant star, and then decelerate to land back on Earth. Acceleration is absolute. It can be felt. The traveling twin feels g-forces during the turnaround. So, their frame of reference is not inertial for the entire journey. This breaks the symmetry. The calculations, when done carefully taking the acceleration into account, consistently show that the traveling twin is the one who ages less. There is no paradox. The twin who undergoes the acceleration is the one whose life is shortened from the perspective of the universe. Another deep question is, what is really happening? Is time actually slowing down, or is it just an appearance? The answer from physics is that it is real. It's not an illusion. The muons really reach the ground. The GPS really works. The atomic clocks on jets really show a discrepancy. The flow of time is not absolute. It is a personal, local experience. There is no universal now that applies to everyone. Your now and my now are only the same if we are in the same place and not moving relative to each other. As soon as we are in relative motion or at different gravitational potentials, our nows slip out of alignment. This leads to the concept of the relativity of simultaneity. Two events that are simultaneous for one observer may not be simultaneous for another observer moving relative to the first. This is another direct consequence of the constant speed of light. It further shatters our classical notions of a universal flowing time. Let's explore the connection between time dilation and another famous relativistic effect, length contraction. We mentioned it briefly with the muons. Just as time stretches, lengths contract in the direction of motion. So, if a spaceship 100 meters long flies past you at 87% of light speed, you would measure its length as only 50 meters. From the perspective of the astronaut on the ship, their ship is still 100 meters long, but you, rushing past them, would appear squashed by half. This is how the muon sees the atmosphere as thin enough to traverse in its short lifetime. Time dilation and length contraction are two sides of the same coin, ensuring that the speed of light remains constant for all observers. Now, let's go deeper. Why does this happen? What is the fundamental nature of reality that makes time behave this way? The answer lies in the geometry of space-time. In 1908, the mathematician Hermann Minkowski, who had been one of Einstein's professors, realized that special relativity could be best understood as a theory of a four-dimensional universe, 3 dimensions of space, and 1 dimension of time, woven together into a 4-dimensional space-time. In this picture, every object has a world line, a path through space-time that traces its history from birth to death. A stationary object has a world line that is straight and vertical in the time direction. A moving object has a world line that is tilted. The crucial point is that in this 4-dimensional geometry, there is a quantity that is absolute, that all observers agree on, just like in ordinary space. The distance between 2 points is absolute, regardless of how you rotate your coordinate axes. In space-time, this absolute quantity is called the space-time interval. It's a combination of spatial distance and time separation. For two events that are separated in both space and time, different observers will disagree on how far apart the events are in space, and they will disagree on how much time elapsed between them. But they will all agree on the space-time interval between the events. Think of it like this. You have a ruler. You can hold it horizontally and measure its length. You can hold it at an angle, and its shadow, its projection on the floor, will be shorter. The actual ruler length is the invariant. The projections are what change. In space-time, the ruler is the space-time interval. The projections are the separate measurements of space and time that different observers make. Time dilation and length contraction are the effects we see because we are projecting the absolute space-time reality onto our personal, relative concepts of space and time. One observer's, mostly time measurement, is another observer's mix of space and time. This is a profound shift in thinking. Time is not a separate, universal river. It is a dimension, much like the spatial dimensions. Your now is like your here. It's a personal, local concept. General relativity takes this geometric picture and makes it dynamic. Space-time is not a static stage. It is a flexible, malleable fabric that can be curved, stretched, and warped by the presence of mass and energy. Gravitational time dilation is simply a manifestation of this curvature. Clocks run at different rates at different points in a gravitational field because the fabric of time itself is stretched. This leads to some truly mind-bending implications. One is the possibility of time travel to the future. It's not science fiction. It's engineering. If you could build a spaceship that could travel at a significant fraction of the speed of light, or one that could hover near a black hole for a while, you could come back to Earth to find that centuries had passed. You would have effectively jumped into the future. There's no known law of physics that prevents this. The problem is the coming back part, which requires turning around, and the immense energy required. Traveling to the past, however, is a much trickier proposition. General relativity does allow for theoretical constructs like wormholes, bridges through space-time, and closed time-like curves, paths that loop back on themselves in time. But these are highly speculative and almost certainly require forms of matter with negative energy density, which may not be possible. Most physicists believe that the universe has some form of chronology protection conjecture that prevents paradoxes, like going back and killing your own grandfather, from happening. Let's talk about the human experience. What would it feel like to be on a spaceship moving at near light speed? From your perspective inside the ship, everything would seem normal. Your clock ticks 1 second per second. Your heart beats at its usual rate. If you looked out the window, the universe would look very strange indeed. A combination of 3 effects would alter your view. The Doppler effect, which would cause the light from stars ahead of you to be blue-shifted and intensely bright, and stars behind to be red-shifted and dim. Aberration, which would make it seem like stars are crowding in front of you. And of course, time dilation of the external universe. As you accelerated, you would see the clocks of the entire universe speed up, their light shifting to higher and higher frequencies, their processes happening faster and faster. You would, in a sense, be watching the future of the universe unfold in fast forward. The journey to a star 100 light-years away might take you only a few years of your personal time, but you would see the light from that star, carrying 100 years of its history, rush past your window in those few years. Now let's connect this to the very large and the very small. On cosmological scales, the expansion of the universe is governed by general relativity. This expansion also affects the flow of time. From our perspective, the light from extremely distant galaxies is not only redshifted due to their motion away from us, the Doppler effect, but also due to the expansion of space itself, stretching the wavelength of the light. This cosmological redshift is related to the stretching of time in the expanding universe. It's a deep and active area of research. On the quantum scale, we have a problem. General relativity, our theory of gravity and the large-scale universe, and quantum mechanics, our theory of the atomic and subatomic world, are fundamentally incompatible. They are both spectacularly successful in their own domains, but they cannot be merged into a single, coherent theory. This quest for a theory of quantum gravity is the holy grail of modern physics. In theories like loop quantum gravity or string theory, the nature of time becomes even more bizarre. Some approaches suggest that time, like space, might be quantized. It might come in discrete, indivisible chunks, a smallest possible unit of time, sometimes called the Planck time, which is about 10^43 seconds. At this scale, the smooth, continuous space-time of general relativity might break down into a frothing, chaotic foam. The very concepts of before and after might lose their meaning. This is the frontier. We have followed the thread of time dilation from a simple light clock on a spaceship to the edge of known physics, where time itself may be an emergent property, not a fundamental one. So, where does that leave us? We began with the subjective psychological experience of time, how it can fly or drag. We discovered that this fluidity is not just in our minds. It is woven into the very fabric of physical reality. Time is not a rigid external master. It is a flexible, personal, and relative participant in our lives. The steady tick-tock of a clock is a comforting illusion, a local phenomenon. Out there in the cosmos, time is a wild and variable thing. It slows down in high-speed rockets. It crawls in deep gravitational wells. It stretches with the expansion of the universe. The now you are experiencing is yours and yours alone. It is synchronized with the people immediately around you, but it slips out of sync with someone on a distant planet or someone moving past you at high speed. This understanding is humbling. It tells us that our common sense view of the world is just a small, slow-motion slice of a much richer, weirder, and more wonderful reality. The universe is not just stranger than we imagine, it is stranger than we can imagine. But it's also empowering. Every time you use a GPS device, you are touching this profound truth. The ability to navigate our world rests on our understanding that time is not absolute. The laws of physics, which allow for such bizarre phenomena, are also what make our modern technology possible. So, the next time you feel a moment drag on or slip through your fingers like sand, remember that you are experiencing a tiny personal echo of the cosmos's greatest secret. Time is not a river flowing at a constant rate. It is a vast, malleable ocean with currents and tides, whirlpools and eddies. We are all sailors on this ocean, each in our own little boat, with our own clock, navigating the strange and beautiful waters of space-time. And with that, our journey is complete. We have turned over every stone we set out to find, from the failed search for the ether to the bending of light, from the ticking of a light clock to the frozen horizon of a black hole, from the geometry of 4 dimensions to the quantum foam at the edge of understanding. We have seen it all. The mystery of time dilation is no longer a mystery, but a testament to the power of human curiosity and the breathtaking elegance of the universe we call home. Good night. Have a deep, calm sleep.